Hi guys, good morning. Shall we start? Is everyone ready?
Yes, sir.
Right. So we were doing chemical kinetics, isn't it? Right. We saw what do you mean by rate of a chemical reaction, right? So can someone tell me what exactly do you mean by rate of a chemical reaction? How do you define it? I'm asking.
Rate
Yeah.
of reactants decreasing and rate of products increasing.
Okay. So that happens during a chemical reaction. Obviously, the rate, not the rate. Basically your concentration of products increases and then the concentration of reactants decreases, right? So I'm asking, what is the rate formula generally? R is equal to what?
Delta C by delta T.
That's it, very simple. So basically when I say rate, we speak in terms of rate of change of concentration, how the concentration is changing, how fast the concentration is changing, either the concentration of reactant or the concentration of products. How is it changing, how fast it is varying? That is what is the rate of the chemical reaction, right? Okay, so we connected this rate of the chemical reaction with respect to rate of disappearance of products, and I'll be able to connect them also with rate of formation of rate of disappearance of reactants and rate of formation of products, isn't it? And I think if I have a general equation like this, AA plus BB gives CC plus DD, right? So hope you remember how I'm able to connect the rate of the overall reaction with respect to A, B, C, D. Hope you remember what we even did a problem. So I say rate of the overall reaction, right, will be equal to minus 1 by A dA by dt, right? What is this dA by dt called as, guys? What is this dA by dt called as?
Rate
Minus
of
dA by dt.
disappearance.
Rate of disappearance of A, correct? So this dA by dt, this talks only about the change in concentration of A. So this particular term is going to give me rate of disappearance of A, right? Now how this rate of disappearance of A is connected to rate of the reaction? It's equal to 1 by A into rate of disappearance of A. Rate of the overall reaction is equal to minus 1 by A into dA by dt, where dA by dt is the rate of disappearance of products. Now, same way I'll be able to write for B also. So it's minus 1 by B into dV by dt. Again, dV by dt is the rate of disappearance of B, right? And hope you understand why am I putting a negative sign in if I come to reactants. Basically, is because the concentration of reactants are decreasing along the course of time. That's why, right? And then if I go to products, now I don't have to put a negative sign. It's plus, and it's 1 by C dC by dt, where dC by dt is the rate of formation of C, and 1 by C into dC by dt will become equal to the rate of the chemical reaction, right? And same way, it's equal to 1 by D into dd by dt. So where the dd by dt is the rate of formation of D, and 1 by D into dd by dt will become equal to the rate of the chemical reaction, right? Right. So you would have understood why am I putting this A, B, C, D and all these into this picture, because I gave you the reaction. Like I gave you an example for formation of water, H2 plus O2 giving H2O. And then we saw how actually stoichiometric coefficients affect the rate of the reaction, right? So how the stoichiometric coefficient affects the rate of the reaction, or say the rate of disappearance of products and reactants or formations, all these things, right? So we'll do more problems on this, and then we'll continue with the next concept. Right. So the question goes like this. So I have two SO2 plus O2 giving 2SO3, right? Fine. First take on the reaction, I'll give you the question. Right, the question. In the reaction, rate of formation of SO3, rate of formation of SO3 is 100 kg per minute, right? Rate of formation of SO3 is 100 kg per minute. They're asking, find the rate of disappearance of SO2 and O2. Find the rate of disappearance of SO2 and O2. So the rate of appearance or rate of formation of SO3 is given. They're asking you what is the rate of disappearance of SO2 and O2. Okay, so what is the answer?
Rate of disappearance of O2 is 50 kg per minute.
Okay.
The rate of disappearance of SO2 is 100 kg per minute.
Yes, correct. Right. Now, very simple. Now, how will I write this equation? Rate of the overall reaction is equal to, can I write it like this? Minus 1 by 2 into d SO2 divided by dt is equal to minus 1 by 1 d O2 divided by dt is equal to plus 1 by 2 into d SO3 divided by dt. This equation I can write, right? So what is given in the question? They have given this value, rate of appearance or rate of formation of SO3, and this value is given as 100, right? This value is given as 100. So what they're asking this value and this value. They're asking this value and this value. Now it is minus 1 by 2, here it is plus 1 by 2 dt by dt, right? So can I say this value basically, okay, it's not this entire value, it's this value they're asking, that is rate of disappearance of SO2 is what is they're asking. So 1 by 2 here, 1 by 2 here, so I can directly say that this is also going to be 100, but it is going to be minus 100. That's the only difference, right? Because it is reactant, I have to put a negative sign, so it is minus 100 kg per minute, right? And if I go to SO2, so I'll write it as minus 1 by 2 into 100, that is this, right? 1 by 2 into rate of formation of SO2 is equal to minus do by dt, is equal to minus do by dt, right? So now what will be this value then? It will be 1 by 2 of this, so it is going to be 50 kg per minute. That's the answer, right? So guys, everybody understood? Sachin, Lakshya, Kailash, Hatni, everybody understood? Ashish?
Yes, sir.
Right? Is there any doubt how this problem came, how the answer came?
No, sir.
Okay, fine. Right. So yeah, this is how the questions will be asked. You have to be very, it's a very simple problem, but you just have to understand how are we going to use this rate of formations and rate of disappearances and connect them with the rate of overall reaction. How are we going to do it? That and all we'll be able to do. Okay, so we'll move on to the next concept. And yeah, tomorrow is your test, isn't it, for electrochemistry? Have you heard the news?
Yes, sir.
Yes, sir.
Okay, so prepare well, right? So you have not like what to say, you have not attended my question paper as such, so it will be a very standard question paper. It will not be like summa formulas, just substitutions, like just definitions. It will not be like that, right? So prepare nicely. Okay. So we'll move on. Okay, so now we understood how with respect to the concentration of reactants and with respect to concentration of products, I'll be able to find the rate of the chemical reaction, isn't it? Now there is one more way, right? There is, I would say, there's one more mathematical way by which we'll be able to find this rate of the reaction, right? So there is going to be one law which you already studied, I guess, in your 11th class, and that law again is going to help us here, right? So the law is law of mass action. Do you remember this law? At least can you tell me which chapter did you study this law of mass action in 11th class? Guys, do you remember what is this? You would have studied this in your 11th chapter, 11th, one of the 11 chapters. Can you, okay, maybe you don't remember what is the law, but can you please remember and tell me what was the chapter which you studied this?
Equilibrium.
Good. Basically, you have studied this in equilibrium, right? So the entire equation, like you have an equation for Kc, isn't it? You write it as A power B power, I mean D power D into C power C divided by A power A into B power B, all that. So basically, this comes from this rate of, I mean, law of mass action only, right? So law of mass action generally talks about the rate of a chemical reaction. It's actually designed for chemical kinetics, but we know how equilibrium constants, that is my Kc or Kp values, are dependent on the rate constant. Okay, you don't know what is rate constant yet. So there are going to be some constant values here also we are going to get, right? So the equilibrium constant is basically decided, or say it is derived from this law of mass action, derived from the rates of the chemical reaction, right? Okay, so we'll see it. So we'll take to the statement first. Take to the statement, law of mass action. Then we'll see what is this. Right, take down. The rate of a chemical reaction, the rate of a chemical reaction, the rate of a chemical reaction is directly proportional to the rate of a chemical reaction is directly proportional to the product of active masses of reactants is directly proportional to the product of active masses of reactants raised to some powers, is directly proportional to the product of active masses of reactants raised to some powers, right? So this is the statement, rate of a chemical reaction is directly proportional to the product of active masses of reactants raised to some powers, right? Okay, so we'll see what is this. Okay, so what the law says is, say if I have a reaction like say AA, some A plus B giving products is a reaction, some reaction which I don't know what exactly is this. Okay, some general reaction I have, right? Okay, so what the law says is the rate of this particular reaction R right, is directly proportional to the product of active masses. So first you have to understand what are these active masses. So nothing, active mass, say for, like, see, understand, say I have some, like in a reaction I have some 100 grams of the reactant. Okay, so I have some 100 grams of the reactant. So ideally speaking, in real life situations, you will see that not all 100 grams of the reactant is going to take part in the chemical reaction. Say out of the 100 grams, maybe 80 grams or 90 grams or even 95 grams will take part in the chemical reaction, right? So active masses speak about what is the actual amount of the reactant taking part in the chemical reaction. That is how I exactly define it, active masses. Active masses are defined like this, how they are the actual amount of reactants taking part in the chemical reaction. What is the actual amount? Even though I have total amount something, out of that, how much is actually taking part in the chemical reaction is what is spoken by your active mass, right? And this active mass is a misnomer. What do you mean by a misnomer? Means like from the name you understand something, but it is not exactly that. Active masses are not exactly masses, right? Mass can also be so we generally say it's the amount of reactant, correct? And this amount can be in any form. So it can be mass, it can be concentrations, it can be partial pressures when it comes to gases, right? So all these things are there. So generally active masses, right? Generally active masses, if it is going to be in terms of an aqueous solution, I take the molarity, right? I take the molarity as the active mass, whatever is the molarity as the active mass. And if it is going to be gases, I take the active mass as partial pressures, right? And one important thing which you have to know is when I have pure solids or pure liquids, their active mass value is 1. You have to please understand this, right? Whenever you have pure solids or pure liquids, I do not include them in my equation. Basically, I'll just put the value as 1. Okay, so this you have to do. For example, if in a chemical reaction like this, say I have Fe plus HCl, give some products, whatever the products are, right? Now look at this in Fe, it's in solid state. Fe is in solid state. So you say, for example, if I'm going to write the Kc for this, the equilibrium, your equilibrium constant for this, so what will be the product? I will basically form FeCl2 or FeCl3 plus hydrogen gas will be evolved, right? So for this reaction, if I write my Kc, I'm talking about the equilibrium constant, right, which is studied in the 11th class. What will you write? It will be generally products by reactant. So it will be basically concentration of FeCl2 into concentration of H2 divided by concentration of HCl. Now I have one more reactant also, that is my ion, but it is in solid form. So that for the in place of that I put 1, right? So pure solids and pure liquids are not taken into the Kc equation or even whatever the equation which you're going to see now. For their active masses value is 1. There is no constant. There is no question of molarity. There is no question of partial pressures if I'm going to have pure solids or liquids. So I substitute their values as 1. Is that okay? Right? So you have to know about this regarding the active mass, right? Okay, so now we'll go back to the law statement, right? So what it says is, for example, if I have a reaction like this, A plus B giving products, right? So it says that the rate of this overall chemical reaction is directly proportional to the product of active masses of reactant. Basically, there are 2 reactants here, right? So I have to take the product of these 2 reactants is what? I have to take the product of active masses. And again, the active mass will depend on the phase of the reaction. So assuming that these are aqueous solutions, and assuming that these are aqueous solutions, I'll be able to write this as concentration of A into concentration of B, because they say it is product of active masses of reactant, right? And they say these 2 terms, so that is the concentration of A and concentration of B, is is actually raised to some powers, and I don't know those powers, so I'll just put it as X and Y. Power of A is X and power of B is Y. We'll see what exactly are these powers talking about in a few times. Just wait for it, right? For now, we're just looking into the statement, what it says, right? So it says that the rate of the chemical reaction is directly proportional to the product of active masses of reactant. So I'm taking the product of concentration of reactant. There are 2 reactants here, right? And they say that product of active masses of reactant raised to some powers. The powers are X and Y. We'll speak about it later in a few while. Wait for it. So now I'll be able to rewrite this equation. So I'll be able to rewrite this equation if I put a constant. So I can write it as K into A power X into B power Y. Right? K is equal to R, R is equal to K into A power X into B power Y. Okay. Right. Now this K, this K is what is called as rate constant. Right? This K, which I'm putting as the proportionality constant, is what is called as my rate constant, and it's very, very important. Right? Okay, and this X and Y, what we write here, again, we'll see what is it, but I can just give you the names of what are they called as, right? So this X is what is called as order with respect to A, and Y is the order with respect to B. And if I sum them up, that is, if I write the sum of x plus y, say I am going to get some value as n, and this n is what is called as the overall order of the reaction, of the total reaction, right? So you have to know this. So this x is what is called as order of the reaction with respect to A, right? Only with respect to A, right? And B, y is the order of the reaction with respect to B, only B. And if I write the sum of these two powers, that is, if I take x plus y, and that is going to give me n, and this n is what is called as the order of the overall reaction. Okay, order of the overall reaction, right? So this is what is called as the rate equation for any reaction, right? This particular thing is what is called as rate equation, or it is also called as rate law. So this law of mass action, it is also called as rate law, right? And this equation which I write here, R is equal to K into A power X into B power Y, it is called as rate equation, or it is also called as rate law equation. Anything is fine. It is also called as rate law equation. Okay, fine. So now we have to study about this constant which is here, right? I have to study about this rate constant K. So hope you understand. Okay, at least now do you remember what was the connection between this K, which I write here, and the equilibrium constant? Do you remember, guys?
Yes, sir.
What is the connection?
I'm not exactly sure, but like equilibrium constant is concentration raised to its stoichiometric numbers by products by reactants, I think.
Okay, fine. Do you want to know about it, guys? Do you want to know about how this rate constant is connected to the equilibrium constant?
Yes, sir.
Okay, cool, fine. So when I go to equilibrium, right? So I think I already denoted in the graph where exactly we are going to calculate equilibrium from, like, or exactly where I'm going to visualize equilibrium from. So if you remember the graph, I had graph like this, concentration here, time here, right? So this was the graph I was speaking about. So there are going to be two graphs, obviously one for reactant, which will be a decreasing curve, and another for products, which will be an increasing curve. So you would have got something like this. So this would have been for reactants, and this would have been for products, right? So until this point, the concentration of both the reactants and products are varying, right? So after this point, what you see? After this point, what I'm seeing is that the both the curves are attaining saturation. That means what? The concentration of reactant and concentration of products are not changing with respect to time, or not changing with respect to time, right? Now, how do I define equilibrium, right? Can you tell me this answer? How do I define equilibrium with respect to rate of the reactions? Do you remember, or someone taught you? How do I say there is one certain condition regarding the rate, right? And only if that condition is satisfied regarding the rate, I say equilibrium is attained. What is the condition?
The forward and backward rates are equal.
Correct. So remember this. So whenever equilibrium is attained, when I say equilibrium, at equilibrium, right? Say if I have a reaction like this, A reversibly giving B, that means A can form B, B can also form A if the situations are suitable, right? Okay, so at equilibrium, what happens is, this is how I define equilibrium. At equilibrium, the rate of the forward reaction is equal to the rate of the backward reaction. Rate of the forward reaction will become equal to the rate of the backward reaction. This is what you have to understand by what happens in equilibrium. At equilibrium, the rate at which A forms B will be equal to rate at which the B forms A. That is why you're seeing that the overall concentration is not changing, right? So if at all I see that the rate of forward reaction is greater than the rate of backward reaction, which side the reaction will occur? It is going to move through the forward direction, because the rate at which A forms B is higher than the rate at which B forms A. So there basically you can say that more and more amount of B will be getting formed, right? And say if I say that RB is greater than RF, that means what? Now B is capable of forming A in a more faster way than the vice versa, than A forming B. So during the course of the reaction, you will see that the concentration of A is increasing, isn't it? But at equilibrium, the rate of the forward reaction becomes equal to the rate of the backward reaction, right? Becomes equal to the rate of the backward reaction, and then only I say that equilibrium is reached. And that's the reason why you see that the concentrations of reactants and products are not changing after this, because the rate becomes equal. Say I have 2 grams of A converting into B in 1 second. You will see that the same 2 grams of B will come back in 2 seconds into A. So you can understand what do you mean by rate of forward equal to rate of backward reactions, right? Okay, so if this happens, so if this particular condition happens, that is rate RF is equal to RB, we'll see what is going to happen, right? So we'll just do a very small derivation for your equilibrium constant from this, right? Fine. So let me take this reaction only. Let me take this reaction only. Okay, fine. So how will I write RF for this from the rate law? From the rate law, I can write it as R is equal to K into, now what is the reactant for the forward reaction? For the forward reaction, A is the reactant. We are speaking only about reactants here in the rate law equation, correct? So A is the reactant. Say I have some AA gives BB, say A power A I have. Okay, fine. Now how will I write the backward reaction? Now for the backward reaction, which is the reactant now, the reactant is B, the product is A for the backward reaction, right? For the backward reaction, the reactant is B, right? So now the rate constant also would have changed. So if RF is equal to KF into A power A. KF is the forward rate constant. You can see this K I'm speaking about, right? So here it is KF. Here it is KF. And for RB, that is the rate of the backward reaction, when B becomes the reactant, it will become KB into concentration of B raised to some power of B. Right? I'm just writing this from rate law. Right? The R is equal to K into A power X into B power Y, where here for the forward reaction A is the reactant, and for the backward reaction B is the reactant. Right? Now when I go to equilibrium, so this will be changing, like obviously until equilibrium is attained, these two values are not same, right? But once I reach equilibrium, right? Once I reach equilibrium, I see that the rate of the backward and rate of the forward reactions are equal. So these two I'll be able to make it equal. So if I do that at equilibrium, I can write Kf into A power A is equal to Kb into B power B. Now this happens only at equilibrium, guys. Please understand. So whatever the concentrations of A and B which I'm writing here, they are concentrations at equilibrium. After the equilibrium is reached, what is the concentration of A and B? That concentrations only we'll be able to write here. But if at all it is going to be a normal rate law like this concentrations of A and B can be in any point of time. At equilibrium, starting point, middle point, it can be any time. Right? But here, if this particular case at equilibrium, if it comes, you have to write the concentrations of A and B when they are in equilibrium. What is the concentrations of A and B at equilibrium? That concentration value only you have to substitute here. Anyways, right? So this is the equation which we get at equilibrium, RF equal to RB. Right? So now if I take the ratio of the rate constants, that is if I write Kf by Kb, now what do you see here? It will become B by B divided by A by A, right? So what do you see here? This ratio of the forward rate constant and the backward rate constant is what is my Kc. You have to know this, right? This ratio of forward rate constant and the backward rate constant is what is called as my Kc. And you can see that the Kc is equal to products raised to the powers divided by reactants raised to the powers. This is how I get the equation for your equilibrium constant with the help of your rate law. So if someone asks you, what is this equilibrium constant? Just tell them that it is the ratio of the forward rate constant and the backward rate constant. Kf by Kb is what is the equilibrium constant. That is equal to products divided by reactants raised to their stoichiometric coefficients. Guys, everybody understood the derivation, what we did here?
Yes, sir.
right? Is there any
Yes, sir.
doubts? We did nothing big here. I just gave you the rate law, and I told you that at equilibrium the rate of forward reaction is equal to the rate of backward reaction. So for the forward reaction, A is the reactant. For backward reaction, B is the reactant. So I just equated them both, and I told you that the Kc is nothing but the ratio of forward rate constant and backward rate constant, and that is equal to products power stoichiometric coefficient divided by reactants power stoichiometric coefficients. That's it, right? Okay, so this is how the rate constants are connected with equilibrium. You should have studied this in your previous class, but still now you learned it. It's good, right? Okay, so we'll move on about more about this. Right. So we look at this properties of K. Right. What are the properties of this K rate constant? Right. So please understand that the rate constant is independent of the initial concentration of the reactant. I would say it is independent of the concentration itself, not only initial concentration. It is independent of the concentration of reactants. That is not like if I change the concentration values of, if I change the values of A and B, right? R value will change definitely. Rate of the reaction will change, but rate constant will not change. Right? It is not going to depend upon the concentration of the reactant, right? But what it is dependent on? It is definitely dependent on temperature. Right? It is definitely dependent on temperature. So the next part of the chapter, right? The next part of the chapter, what will you see is, you will see how if temperature varies, my rate varies. That is the rate constant varies. Right? That will be the next part of the chapter that we'll see later. So you can see that temperature does affect the rate constant value, right? Okay, and also it is affected by putting a catalyst. It is also affected by putting catalyst. I know catalyst can alter the rate of the reaction. They'll make it faster or they'll make it slower, right? So obviously it happens because there is going to be a change in K value, right? And obviously change in K value will have a change in R value, right? So yeah, so it is independent of the concentration of reactants. It's not reaction, it is reactants, right? And it is dependent on temperature, as well as if any catalyst are there, it is going to depend on that also, right? Okay, so if you ask me what is the unit of rate constant, right? What is the unit of rate constant? Like, see, I will write a simpler equation rather than having two reactants. I write it like this: K. Say I have a reaction like reactants giving products, a very simple reaction I have, right? I have a reactants giving products, a simple reaction I have. Say it's K into R power N, right? N is the order, overall order, obviously. With respect to R also it's same. The overall order is also same. So N is the order of the reaction here, right? So I know, see, we are doing this for finding out the unit of rate constant, isn't it? Okay, so I know R is mole per liter per second, right? That is what is the unit of rate. Is it because it is change in concentration by change in time? Change in concentration mole per liter divided by second, so it's per second, right? And I know what will be the R value. That is, R is in terms of molarity, right? So molarity, basically it's mole per liter, right? But I have a power also, right? I have a power also. So I will write this whole power N, right? This whole power N is what is the overall this thing unit here, right? So I have mole per liter power N. So what I have to find? I have to find the unit of rate constant. So I can write K is equal to mole per liter per second divided by mole per liter the whole power N. That is what will be the unit of the rate constant, right? So now how will I take it? So can I write it as, here I have mole power 1, here I have mole power 1, here I have mole power N, and if I take it to the numerator, what will happen? It will become mole power 1 minus N. So I have mole power 1 minus N, right? Okay, next. I have liter power minus 1 here, and I have liter power minus 1 into N. So basically I have liter power minus N, isn't it? I have liter power minus N. So when this liter power minus n goes to the numerator, it will become a liter power n plus n. So it now L will become liter power n minus 1, because I already have a minus 1. I have a minus n here. N goes to the top, it becomes plus n. Right? And what is remaining? Only second power minus 1 is remaining. So this is the unit of K. Now obviously it is going to depend upon what is the order of the reaction. Right? The unit in the mole power 1 minus n, L power n minus 1, S power minus 1 is what is the unit of rate constant. It is going to depend on the order of the reaction, definitely. Right? Say for example, if it's going to be a 0th order or first order reaction. Actually, I told you we'll speak more about this order, right? But just understand for now, say if I take the 0th order reaction. What do you mean by 0th order reaction? N is equal to 0, right? 0th order reaction means N is equal to 0. So now what will happen? Can I say it will be exactly like mole per liter per second? That is the unit of K. Now you can understand from this, if I write R is equal to K R power, now N is 0. Now what will happen then? The concentration term itself is not there, right? So the rate becomes equal to K, right? The rate becomes equal to K. So obviously unit also will be similar. Rate, I know it's mole per liter per second, and it is equal. K also will have mole per liter per second, right? So when I go for first order, what will happen? Now if I put N is equal to 1, if I put N is equal to 1, 1 minus 1 will become 0. 1 minus 1 will become 0. So for a first order reaction, the unit of rate constant is per second. That's it. Because mole power 1 minus 1, 0. Again, 1 minus 1, 0. S alone is remaining. So the unit of rate constant is, what is it? K, second power minus 1 is what is the unit of rate constant. Right? Okay. So I think you understood what is this K value, right? And what are the properties of this K value? What are the units of this K value? So unit of K is going to depend upon the order of the reaction. That is understood, right? Okay. Now we'll move on. We'll move on to see what exactly is this order of a reaction, right? We'll move on to see what exactly is the order of the reaction. Okay, fine. So guys, any doubts till now? Is everything okay?
Yes, sir.
Yes, sir.
Sir.
Cool. Right. So we're going to see what is this order. Okay. So, so you can understand that from the rate law equation, if I write it like this, R is equal to K into R power N, where N is the order and K is the rate constant and R is the concentration of the reactant. Cool. Right. So when I write this, right, so you can see that the rate of the reaction, how is it connected to the concentration of the reactant, right? So you can see that it is directly related. That is understood, right? R is directly proportional to R power N. That I understand. If I increase the concentration of the reactant, the rate also will increase. That is understood. But how exactly will it vary? Say if I increase the concentration of the reactant by 2 times. Say initially I had 1 m, right? Now I'm increasing the concentration by 2 m, right? How much will be the increase in the rate of the reaction? Like these kind of questions can be asked, isn't it? Say if I double the concentration of reactant, how much will be the increase in the rate of the reaction? Like that, or say tripling or half, whatever it is, whatever I'm going to do to the concentration of reactant, there is going to be some change in the rate of the reaction also, right? And obviously, it is not only about changing the concentration of reactant. You have to understand what is this N value. Like depending on this N value only, say for example, if N value is 1, for example, if N value is 1, that means what? If I double the concentration of reactant, I can say that the rate also will be doubled because it is linearly related, just a straight line equation, right? If it's 1, if nothing is there, right? So if I double the concentration of reactant, there will be doubling of rate also, right? But what if the power is 2 or the power is 3 or power is 0.5 or say it's 0.33? It can be anything, right? So this order decides how the rate is varying with respect to the concentration of reactant. Very, very important. So you can see that this determines the order determines how rate is varying with respect to the concentration of reactant. So if I change the concentration of reactant, right, how the rate will vary will be decided by the order, right? If I change the concentration of reactant, right, how the rate will vary is determined by the order of the chemical reaction. Okay, fine. Now, how will I be able to find the value, right? How will I be able to find the value? Now, it's very simple. There are a few ways by which we'll be able to find the order of the reaction, right? So, one simple way I'll tell you now, right? This now simple way is now you definitely understand that the rate is varying if I change the concentration of the reactant, right? What I'm understanding is the rate is varying if I change the concentration of reactant, right? So there is a graphical way by which you will be, it's not graphical, it's actually I would say experimental way by which you will be able to find this order. We'll be able to find this order. Okay. Say now the graph I'm going to plot is going to be between the rate and the concentration of the concentration of reactant R. Right? I'm going to plot a graph between the rate of the reaction with respect to the concentration. So obviously I'm going to see if I increase or decrease the concentration, how the rate of the reaction is varying. Okay, fine. Now let me ask you a question. Now I can do this, right? Generally I will only be changing the concentration, right? Now rate can be calculated in some other methods. We'll not go into much into it. So please know that I will be able to calculate rate somehow, right? And I am only changing the concentration of the reactant. So this graph can be easily plotted, right? Because I know the rate value for each and every change in value of R, the rate value is going to change, and that can be recorded. Okay, and I'll be able to get a graph, right? So depending on how the shape of the graph looks, right? Depending on how the shape of the graph looks, I will actually be able to predict what will be the order of the reaction. Again, I repeat. So if you plot this graph, right, there is going to be some curves coming here, right? So depending on what is the shape of this particular curve which I'm going to get here, I will be able to predict what is the order of the reaction, right? So let me see, you are a little smart enough. Let me ask you a question, right? So if I get a graph like this, right? If I get a graph like this, can you tell me what is the order? Think properly and then tell me. I am plotting the graph between rate and the concentration, right? And I'm seeing that I'm getting this kind of graph. So can you use your mathematical skill? No, it's not mathematics, it's logical. Can you use your logical reasonings and tell me what is the order here?
Sir, is it 0?
Very good, very good, very good. Yes,
Zero,
it is
sir.
0. Yes, it is 0. So what I understand here is that if even though I'm changing the concentration, the concentration value is increasing, basically increasing or decreasing, but the rate value is not changing at all, right? But the rate value is not changing at all. I had one value, say some x value I had here, and that x value is not at all changing, even though I'm changing the concentration of R. And when will that happen? Only when this n is 0. So I have R is equal to k power R, k into R power n. When this n is equal to 0, what will happen? R will become equal to k. That means what? There is no concentration term at all here, right? There is no concentration term at all here if I have n is equal to 0, and it is equal to the rate constant. That is a constant value, correct? And that constant value is not going to change with respect to the concentration, right? So obviously, if you get a graph like this indicating that the rate is not changing with respect to the concentration of the reactant, I will be able to easily tell that this is going to be a 0th order reaction, or say the order of the reaction is 0. This I'll be able to call it as a 0th order reaction, or say I'll be able to find out that the order is 0. Okay, understood. Fine. Now, if I get a graph like this, what would you say? Okay, now, so fine. Okay, actually, for the graph which you got here, R versus R, so this is for 0th order. Okay, so now if I have a graph like this, R and the concentration, and when I plot a graph, I was getting a graph like this. So now can you tell me what will be the order?
1.
Exactly, right? So now when I have n is equal to 1, what will happen? R is equal to K into a concentration of R, right? Now, does it not look like a straight line equation? Y is equal to mx. X is there in the x-axis. Sorry, R is there in the x-axis. R is there in the y-axis. So what will be the slope here? Slope value will give me what?
1.
Good. 1. Will you get 1?
Y by x.
Y by x. Okay, what is y by x? What is it? If we compare these two equations,
Yeah, k.
very good, right? So slope will get us k. So this is y is equal to mx kind of graph, a straight line equation without any intercept. When I have some c, then some intercept will come. So, but there is no intercept here. So y is equal to mx and r is equal to k into r. So these two equations are similar. So x is there in the x, r is there in the x-axis. The rate is there in the y-axis. So definitely the slope of this line should give me the k value, rate constant value. Okay. Now tell me, I will not draw the graph. If it is a second order reaction, right? If it is a second order reaction, what will be the shape of the curve?
Upward parabola.
Correct. So it's going to be a parabola. Very good. Right? So you will see that if it is a second order reaction, and if I plot a graph that is between R and the concentration, you will see that it is not a straight line, it is actually going to be a parabola. Right? Parabola, you know how it looks. So you know it looks something like this. I'm not very good at drawing, but please bear with it. Okay. So it's actually going to be a parabola. Right? You know how parabola equation is. Y is equal to 4ax squared. Is it correct? Okay, whatever. You can understand that y is directly proportional to x squared. Like the power 2 is there. So only then you'll be getting a parabola. Right? So with this method, so basically if I plot a graph between the concentration and rate and see how the graph is coming, right? If I see this kind of straight line, it is 0th order. If it is a straight line like this, it is first order. If I get a parabola, it's second order. So like this, I'll be able to predict what is the order of the reaction, right? But this method is not that useful, right? When I have say complex numbers like if I have a order of 0.3, right? So it is actually very difficult to find from the graph, right? And you can understand that the order can be easily decided, right? If it is some equation. Okay, so now I think till now, no doubts, right? This is one of the ways by which I'll be able to find the order, right? There are a few more ways by which I'll be able to do it, right? So we'll see what is that. What is the time? Okay, we have 5 more minutes. So I'll just tell you one more thing and we'll wind up, right? Right. So now when I say a chemical reaction, right? When I say a chemical reaction, right? Now it can be classified in 2 types, right? It can be generally classified into 2 types. So first one is what is called as an elementary chemical reaction, right? Or say it's also called as simple chemical reaction, right? And I have something called as complex chemical reactions, right? It is called as complex or even composite chemical reaction. You can even write it here, right? I have elementary chemical reaction and I have something called as complex chemical reactions. So how are these classified is the question, right? Now it is all going to depend upon what is the number of steps which are involved in the chemical reaction, right? What is the number of steps which are involved in the chemical reaction? Based on that, I'll be able to classify chemical reactions into elementary and complex, right? So remember, elementary means it's a single step reaction. Only one step, the reaction is over, right? Only one step, the reaction is over, right? And in case of a complex chemical reaction, it is made up of number of steps, or I would say Okay, fine. It is more than one step process. It is not a single step reaction. It contains more than one step, and you have to understand that each step is an elementary step, right? Each step is an elementary step. So basically, you have to understand this, right? So obviously, whenever I say elementary chemical reactions are having only one step, or like it's a single step reaction, and I would say the better way of putting it of complex chemical reactions is complex chemical reactions are made up of number of elementary steps. That's the best way to put it, right? Elementary reactions are over in single step, right? And for complex reaction, they are made up of many number of elementary steps. That's the correlation between your elementary and complex chemical reactions, right? And the best example I can give you, you already studied in your organic. So elementary step example can be your SN2, single step process, right? And your complex reaction can be an example for SN1 because it has two steps. Say first the formation of carbocation, then the nucleophile attacks in your SN1, right? And same way for in your SN2, what happens? Both the nucleophile attacks and the leaving group leave simultaneously. So both bond breaking and the bond making happens simultaneously, single step, right? So SN2 is an example for this. SN1 is an example for this because it contains more than one step, right? So yes, why did we study about this now? Is because for an elementary chemical reaction, finding out the order is very, very, very easy, right? So again, I'll tell you, for elementary chemical reaction, finding the order is very easy. How easy it is? Remember, if I have a reaction like A plus B giving products, I have a reaction like this, right? And if I want to write the rate law, R is equal to K into A into B, now I have to know what is the powers, right? Now please understand, for an elementary reaction, the order of the particular component is equal to the stoichiometric coefficient, right? The order of the reaction, the order with respect to a particular component, with respect to one reactant, right, will be equal to the stoichiometric coefficient of that particular reactant, right? If it's an elementary step, on and only if it's an elementary step. If the reaction completes in single step, then I'll be able to say that the order of a particular component, order of a particular reaction, right, will be equal to its stoichiometric coefficient. So this particular reaction which I write here, if it is elementary, right, I will be able to rewrite this equation very more simply. I don't even have to find the order. The order of the reaction is nothing but the stoichiometric coefficient, which is A and B here. Small a and small b are the stoichiometric coefficient. And since it's an elementary step, elementary reaction, I'll be able to write the order with respect to A as its stoichiometric coefficient itself, that is A, and I can write the order of B with order of B as the stoichiometric coefficient itself because it's an elementary chemical reaction and the order of B is small b, the stoichiometric coefficient of B, right? But for a complex reaction, we'll not be able to do like this because it is made up of so many number of elementary steps, right? So it's a little problematic when I go to complex reactions, right? Fine. So like it say, but in a complex reaction, I'll be able to little make it easy, right? Little I'll be able to make it easy. So since there are so many number of steps, right? Say I have 3 steps in the reaction, right? I have 3 elementary steps in a complex reaction, right? So out of them, one of the step is going to be the slowest step, isn't it? Like one of the step is going to be the slowest step. So rather than concentrating on the other 2 steps which are going to happen like this, which is not going to give me much information, whenever a complex reaction happens, I will try to work only on the step which is the slowest step, right? Whenever a complex reaction happens, I will lay my interest only on the slowest step. So like putting in more technical words, remember for a complex reaction, the rate determining step, it's very important. Like you will not be using this much, but if you go for JE or something, you'll be able to using it, right? So in a complex reaction, the rate determining step is the slowest step, right? The rate determining step is the slowest step. right? So that is basically the slowest step only determines the rate of the reaction. Basically, the order, all these things are basically it is going to depend upon the slowest step only, right? So anyways, it's not much important, but you have to know this. The rate determining step is the slowest step. For example, in your SN1, if I take, there are two steps, right? So obviously first is the formation of carbocation, then your nucleophile attacks. That's what happens in SN1, right? So remember, the rate determining step in SN1 is the formation of carbocation, because to form a carbocation only, it will take more time than the nucleophile coming and attacking the carbocation. Right. So because already the nucleophile is already the carbocation is formed, the nucleophile is attacking is a very fast. It's a quick step, right? But formation of carbocation, that is very very slower when compared to this step. So formation of carbocation in your SN1 is what is your rate determining step. Okay. So I hope you can correlate this SN1 SN2 with this elementary and complex. For an elementary reaction, the order is equal to the stoichiometric coefficient. That's a very simple, straightforward answer, right? But if it is going to be a complex thing, we have to find out which is the slowest step and maybe apply the rate law there to find out whatever the thing which we have to find out. Is it okay? Fine. So we'll continue more about this. Now I'll tell you more and more methods for you to find the order of the reaction. Like this is again second way. The first way is by plotting the graph. By second way is by looking at whether it's an elementary or a complex reaction. There are 2-3 more ways by which you'll be able to find the order of the reaction, right? So that we'll see next class. We'll do more, no problems. So until then, any doubts, guys? Can we wind up?
Sir.
Yeah.
Sir, the solutions question paper I wasn't able to submit last time.
Okay. Okay.
Do you mind if you just correct it for me, sir? Is that possible?
Sure.
I don't know marks. I just want to see if my answers are right.
Okay. Like you can just send it to me. I like maybe because for correcting it, I need some software. Like that is there with Epsilon people. The manager, I have to go there and correct it. But I can tell you whether you have done it correct or wrong. That I can tell you.
Sir. Okay.
Okay, just send me the snapshot of your answer sheet. I'll be able to help.
Okay. Thank you, sir.
Fine. So guys, we'll meet again. We'll do more problems. We'll learn more about this. Right? Fine then. Thank you. Bye bye.
Thank you, sir.
Thank you.
Thank you, sir.
Yeah. Thank you.
Thank you, sir.